Oh, I have to change the title. Yes, let's do that. Oh, whatever, I'll change the title later. Okay, so I'll give everyone a couple minutes to trickle in since I think it is still 8:59. I guess we can start with the most important part of the day. Um, I have two of them here with me in my lap today. This one you'll remember from yesterday, AJ the pirate. This one is Oz. Oz is my oldest one. He's the one who really loves the desert heat. Um, okay, move your head, dude. Oz does not have any teeth, so his tongue just pops out the whole time. So, and he just loves to cuddle in my lap, so he'll be here a lot. Alrighty, so 9 o'clock. Looks like we have at least a few people here. So, let's go ahead and get started. I guess before we do, are there any kind of outstanding questions about the course in general? Or anything so far before we kind of just jump into chemistry? Alrighty, I'm not seeing any. So, I'm going to talk to you about a problem that I had. My toaster isn't working. What should I do? Someone help me, please. Type your stuff. Tell me what I can do to solve this problem. Plug it in. Okay. Cool, cool, cool. All right, I like that. What happens if that doesn't work? What do we do next? Obviously, a very good suggestion. Probably the first one I would do. Okay. Check wall power. I like it. What else can we do? Anything else we can do with this thing? Assuming that both of these are, okay, it is plugged in and the power outlet is indeed charged. Does it turn on? Okay, let's say yes, it does turn on. Okay, we can do that. Check for jam. Okay, let's say it's not jammed. That'd be pretty amusing though, jamming a toaster like, man, how would you do that? Just keep shoving bread in there. Um okay, check the wire. I'll just put that here. Unless you mean like internal wiring. Okay. So, good morning, Paulette. So I'll just tell you right now, I am not qualified to check the internal wiring. Let's say it's not getting warm. No. Let's just do one more solution and then we'll analyze this this thing we're working on. What else can we check with this thing? No one has any more ideas? Okay, that's fine. We can stick with these ones right here. So I'm going to illustrate that we have just done what is called the okay, let's see. I like your ideas. Did I even bother doing this properly? Is it clean? Okay. I like it. Is there toast in there? You guys are just great. Okay. So this is what we can we're going to be able to identify these as steps within what we call the scientific method. This thing that we started with is an observation. We noticed this toaster is not working. All right, and so we came up with some potential ideas of how we might approach this problem or how we might explain this observation. And we came up with what are called hypotheses. So all of these four, and potentially other ones that you guys are writing out, are all hypotheses. These are, what we think might be happening here. So I would, number one is probably the first thing I would do as well, is check if the thing is plugged in. Chances are that's the problem. And this is what's called an experiment. So what we can do is we think, okay, maybe it's not plugged in. That's our hypothesis. So we have in our mind, okay, this might be the reason that this observation is happening. So the toaster is not working because maybe it's not plugged in. So let's try plugging it in. That would be an experiment. So actively going around and maybe unplugging it, plugging it in again, trying things out. That's an experiment. Okay, and we'll do these for all of our hypotheses. Okay, and so we'll go through all of this stuff. Interestingly, when we get to number 4, sometimes we have to have an experiment with other experts. Okay, so maybe I have infinite money. That'd be real nice. And I'm going to call in an electrician to come and look at my toaster. Because, paying however much, like $80 an hour or something to fix, a $20 toaster is worth it in my mind. But, sometimes you have to consult experts. So in my field, I'm a chemist. I'm not an electrician. I don't know electrical engineering. I am not qualified to check out the internal wiring of this toaster. So I might call in an expert. Or I might also check out, maybe the instructor's manual. Not instructor manual, instruction manual, rather. Because chances are maybe someone else has, come up with the same problem and it's in the troubleshooting guide in my instruction manual that came with the toaster. So a big part of science is consulting with what other people have done. So I might go to Google and be like, hey, my toaster's not working. What can I do? That's also, searching what other people have done with this same observation. And so maybe doing all of this experimentation, I find out the heating coils need replacing. And that turns out to be the problem, and now my toaster is fixed. After all of that, doing all of this stuff, we can see all of these hypotheses give us information about the toaster. And all of that, all of our experiments put together and especially, if they agree with other people's results, these two combine together to make what is called a theory. So a theory, in this case, the theory that the toaster needs proper heating coils to function. Kind of a crappy theory, right? But all of these things, anytime we in science have an observation about anything, we do all of these experiments to learn more about it. We put all of this together, all of the information that we get together, along with what other people have gotten about the same problem, and we come up with what is called a theory. So theories in science are going to be kind of explanations for why things are happening, that have a lot of evidence behind them and a lot of people working together to kind of figure them out. Okay, so we do this all the time in real life. You know, we encounter problems and we think of ways we might approach them, and sometimes our results will work. So maybe it just needed to be plugged in and that was the end of it. And then, you know, we have our theory that toasters need electricity to function. You know, could totally be something like that. So theories don't need to be, you know, super crazy and broad, but, you know, something as simple as that can be a theory. All right, in science, we also have what are called laws. So theories, we have lots of evidence, and we kind of have an explanation for what is going on. So we have found out that toasters need electricity to function. We found out that the toaster requires heating coils to function, that it requires proper internal wiring. All this stuff, that is our theory. We have understood, or we have an understanding of the toaster. This is going to kind of stay in place until future evidence comes, and, you know, someone says, you know, I found out a way to make this toaster work without electricity. And again, kind of just a weird example, but that would then cause us to alter our theory. So science is always evolving. We kind of just use as much information as we have to come up with the best explanations for natural phenomena. Okay, so we are trying to explain what's happening. Okay, sometimes we have no idea how to explain it. Something like this might be gravity, for example. We know it exists. We feel it all the time. You know, we know that if I jump, I'm going to come back down again. If I throw a rock, it's going to fall towards the earth. You know, 100% of the time, these things are happening, but we just don't know quite why. So we know gravity exists. We can talk about all the physical formulas that we can talk about, you know, forces and all that stuff, but we don't know why gravity exists. How we have a special term for this. We call these laws. Okay, so laws in science are unexplained. So we don't quite understand them, but we know they always happen. So we know on Earth, on any planet or any, you know, celestial body that has gravity, something that is, you know, placed nearby will go towards the center. That is, you know, irrefutable. So no matter where you are, as long as there is a source of mass nearby, something else will be attracted to it. Okay, look, here's gravity. Boom. Yeah, it worked. Do I know why gravity works? No idea. But we have a law of gravity. That's the difference there. So theories, we have evidence, we have a base understanding of why things are happening. Laws, we do not. Okay, but laws are also irrefutable, whereas theories are not. So theories can say, okay, new evidence has come along, we'll revise our theory. Okay, laws, though, on the other hand, don't really change. We don't have any reason to believe gravity is not going to exist. So that's going to be that. Okay, so all of this stuff is part of the scientific method. So that's how in science we kind of come up with this information that we know. Oh dear, the creature has come in. Creature, come here. Come on, creature. Okay. This one is the embodiment of anger. So let's see if he's going to come forward and yell at us. He's probably one of my favorite of the dogs. He's just very angry all the time. Come here, Preach. So hopefully you can hear him just growling about everything. Yay, creature. He hates being on the television here. He looks like a little gremlin too. Okay, does anybody have any questions, if you can hear me over the growling, that is, about the scientific method? Okay, no questions. Shut up, Creech. I'm gonna put him down for a bit. Hopefully he'll shut up. Okay, cool. So we have met now 3 of the dogs, by the way. So we will be encountering the other 6 at some point. Okay. Cool. So with that in mind, so that is going to be true for all facets of science. We're now going to talk about chemistry specifically. Chemistry is going to be the study of matter and energy. Specifically, mostly we study matter in chemistry. Energy, a lot of that goes into physics as well. So we're going to talk about energy quite a bit, but not nearly as much as we are going to talk about matter. Okay, so does anybody have any idea what matter is? So if I tell you everything in the universe is either matter or energy, let's think of how we can kind of define matter here. Some of you may be tempted to say solid, liquid, gas. That is a part of matter for sure, but that does not necessarily define matter. So if I tell you that, okay, we're getting some fancy explanations here. So we have all matter takes up space. What we've seen here is someone said it has volume. That's the same thing as saying it takes up space. So everything on my desk, everything around me in the air, stuff is taking up space. I'm in this chair right now. Something else can't just come along and occupy the same space as me. Just matter doesn't work that way. 2 things can't really occupy the same spot. All right, anything else that we can talk about matter? Perhaps someone else has read ahead or has some understanding of matter. Creature, stop it. Hey, we have another visitor. Come up here, dude. Come on. Creature, stop it. Okay. No one else has any ideas? Alright, I'll tell you. Alrighty, so in addition to taking up space, alright, I'm gonna go kick the creature out as well. 1 second. Okay, creature, go. You're disrupting the class. Go. So he gets mad when I kick him out as well. Oh well. Yeah, so exactly. So it has mass. So we can see that this bottle cap here takes up a certain volume. It has this space it occupies. And we can also, quantify it. We can say, okay, it's this big. We can weigh it. We can see, okay, it's got this much weight to it. We can figure out its mass that way. So we're going to see that everything that is matter has these 2 properties. So, can anybody think of anything that does not have these 2? Anything that does not take up space and does not have an amount associated with it? Anything at all. I'll give you guys a hint. If it's not matter, it's something else. And maybe there's an example of that something else that you guys can think of. Anything at all? All right, I'll give you a hint. Perhaps that's an example of something that may not take up space or have an amount. I see you guys are just still asleep, huh? All right, fine. I'll do all the work myself. Yay. Oh, okay, time. Now that's an interesting one. Yeah, let's go with the easier answer here. Let's go with, something that it's like not. So this would be something like light. So this would be something like light or heat, something that we can't touch, we can't interact with necessarily. These things don't have space and they don't have mass. So these are kind of just, they're non-corporeal, as it were. Big word there. But everything else, that we're thinking about. So conductivity is actually a property. Electricity we would talk about as energy, but conductivity we're going to see as a property of something. So it's not really something itself. With regards to time, that's a lot more difficult to put in these categories, since time is a really tough one because it's hard to prove it exists. It's not really something we can measure. It's I'm going to leave that for physics class. You guys can deal with time in physics. I don't know enough about time to be able to talk about that. So, in this class, we're going to be talking mostly about matter, but we will be talking about some energy as well. So, let's first talk about matter. So, we've seen that matter is going to have volume, and it's going to have mass. So it's got an amount, and it takes up some amount of space as well. We can see that matter can come in several different types. I'm going to just put a couple of different things out here. And we're going to see if we can't talk about these, and see if we can't analyze these a little bit more. How about a cookie? And how about copper? So if we look at these four things, I've come up with 4 examples of different types of matter. So let's see if we can analyze these. So if we look at these 4 things, what's different about them? Specifically, let's say it's a chocolate, if I can spell chocolate chip cookie. What's different about these 4 things? Specifically, let's talk about water and milk. So let's avoid liquid and solid right now. We will talk about those in a little bit. But just comparing liquid or water and milk chemically. Yeah. Paulette, you're definitely on the right track there. So we're going to see that water is one thing, but milk is going to be many things. And by things, I mean water is just kind of one molecule, right? It's H2O. You've probably heard that before. All of that is identical to each other. So if you have a bottle of water, every molecule of water in that is the same as each other. Whereas in milk, you have water in there, you have some fats in there, you've got sugars, you've got proteins, you've got all sorts of different things in milk. So milk is going to be what's called a mixture. All right? And water is going to be what is called a pure substance. So let's think about the chocolate chip cookie now. Do we think that is made of one thing or many things put together? Many, right, for sure, many. You've got sugar in there, you've got butter. Butter also has a bunch of different things, water, fats, blah, blah, blah. Many things, again. So a cookie is also going to be a mixture. Okay, and how about copper? So just a piece of copper wire. Yeah, definitely a mixture. Absolutely, Lindsay. So a piece of copper wire, what do we think there? Is that going to be one thing or many things put together? One thing, yeah, for sure. Okay, everything in that is copper. They're all the same. We're going to see that that is also a pure substance. So we're going to see that all matter can be classified into these things. So Paulette, I'm going to say one on that. Of course, there are many atoms, but they're all the same. Like copper does not have anything in it besides copper. Like there's no iron in there. There's no water in there. There's no cheese in there. You know, it's just kind of one thing. All right, does that kind of make sense, Paulette? I will assume so. So we can see that all matter can be classified as these two things. All matter is either a pure substance or a mixture. Okay, so we can already look at that, but we can look at them even further. If we take a look even further, let's look at our pure substances. Let's use purple. So our pure substances, we're going to see we can separate those as well. Does anybody know any difference between water and copper? Besides, again, liquid, solid, physical stuff, chemically speaking. Water is different than copper is. I'll give you a hint. That's the formula for water. And this is the formula for copper. Does anybody see differences between those two? Yeah. We're going to see that copper is what is called an element because all of the atoms in copper are going to be identical to each other. Every single atom in that piece of copper is one atom, one element. Whereas in water, that is what is called a compound. That's going to be multiple elements. So anytime you see multiple elements together, that's going to be a compound. If it's just one element, then it's just that element. All right, so we can, if we're given the formula, we can see on the periodic table, if we, we're not going to look at that quite yet, but on the periodic table, we'll be able to find copper if we look at it long enough. However, we will never be able to find water on the periodic table. We can find hydrogen, we can find oxygen, but we cannot find water. Okay, so copper will be an element, water will be a compound because it's made of multiple elements. Okay, so hopefully that makes sense. We'll have plenty of practice with kind of sorting these things in a bit. But let's look at the mixtures in a bit. So we have our milk and our cookie. When you are eating these two things, so let's say we're drinking milk, does our first sip of milk taste the same as the 10th sip, or the 20th sip, or the very last sip? Yeah, pretty much, right? It's going to be the same throughout. It's the same throughout. However, if we eat the cookie, will each bite of the cookie be exactly the same? No, right. Sometimes we may have more chips in one bite than we have in another. Exactly. So this is going to be non-uniform. That means it's different throughout. And so we're going to have fancy words for these as well. We're going to call the uniform one homogeneous. And this one is going to be heterogeneous. So homogeneous means it's all the same throughout it. So presumably the milk will be the same throughout, each sip we take. Or if we're drinking tea or coffee or something, presumably it should be the same throughout. Unless, maybe you put a ton of sugar in your coffee and it's all settled to the bottom or something, then it would not be homogeneous. Whereas something like a cookie or a salad or, something like that, or soup, those are going to be heterogeneous because each part is going to be a little bit different. So if you were to kind of zoom in on one area of the cookie or of the salad, it would be different from another area. But if you zoomed in on the milk, it's going to be the same. So if you zoomed in on milk in one area versus a different area of the milk, they should be the same. All right, any questions on those? I'm going to just kind of clarify this a little bit. Alrighty. So we're going to see that matter we can break apart into mixtures or pure substances. And within those, we have homogeneous mixtures. I know how to spell. And heterogeneous mixtures. And the pure substances, we had compounds and we have elements. Okay, so let's see if we can come up with more examples of all of these things. Can anybody give me an example of an element? Gold. For sure. Anything else? I'll give you a hint. There's 118 of them. Though, of course, you're not expected to know that. And, you will not be required at all to memorize them. So don't worry about that. Mercury. Yeah, another one. Aha. I've tricked someone. Okay, good. Hydrogen. Okay, so I'm going to put this one in red because this one actually does not fit in this category. Does anybody know the chemical formula for salt? Yep, barium would also fit under elements for sure. Aha. So, because this is made of both sodium and chlorine, this would be actually a compound. Okay, because it's got two elements in it. Okay, anything that has multiple elements would be a compound. You're absolutely right, by the way. Sand and water we can go ahead and put is a heterogeneous mixture for sure. Absolutely. So I'm going to go ahead and erase this. So, but we could say sodium is an element, chlorine is an element, for sure. But if we put them together, those are going to be a compound. All right, so let's take some more compounds then, if we're on this. Okay, I have enough elements. You guys are good with elements. Yeah, all of those would be examples of elements. Iron, zinc, carbon. So elements are kind of the easiest ones. You just look on the periodic table. If it's there, it's an element. So you will not find salt on the... Yeah, baking soda would be one. Do you know the formula for baking soda out of curiosity? Yeah, so for example, salt was NaCl, right? Baking soda is this. You'll be learning all of these later. So, if on an exam... Oh, sure. Actually, Ali, we're going to get there in just a minute. So I'm going to hold off on your question right now, if that's okay. Let's just do a couple more compounds, and then we'll go into the sand and water. Yeah. Water would be one. Oops. Okay, let's get two more. Yeah, hydrogen peroxide. So all of these that I'm giving you chemical formulas, by the way, we are not expected to know these right away. Later, we are going to learn how to do these chemical formulas, but right now, if I give you a chemical formula, I would expect you to know that it is a compound. Okay, so if I write, CO2 would be another one. These are all, these are all examples of compounds. So if I give you a chemical formula like this, or something that's obvious like water or salt, I would expect you to be able to classify it as a compound. Okay, so like on an exam or whatever, if I say is H2O a element compound or a mixture or whatever, you should say it's a compound. Okay. Something interesting to note. I'm going to go ahead and just put in the formulas for these elements here. What you might notice, specifically with these two, is some elements normally just occur as pairs. We are going to learn what these are later on in the semester, but these are still elements, okay? So hydrogen, even though it's H2, it's still an element, okay? Because every single atom is the same. They're all hydrogens. However, something like H2O is a compound because it has multiple elements. Okay? Something interesting like sulfur actually occurs naturally as 8 sulfur atoms put together. And that's still an element. It doesn't matter how many there are, because all of them are sulfur atoms. Okay, however, the minute we put oxygen in there or something like that, then it becomes a compound. Okay, so it doesn't matter how many there are, just if there's one element or multiple elements. Okay, questions on elements versus compounds? Okay, so going back up, let's now discuss why salt water would be different from sand and water. What happens when we put salt into water? Assuming we're not like putting a ton of salt into it. We're going to see that all that salt is going to dissolve, right? Right. And so if we were to look at that, we're going to see that that is actually all going to be the same throughout. If you were really weird, you were to take a straw and put it into your salt water, and maybe, your salt water is, In this coffee mug, your salt water is this whole volume. If you put your straw right at the top versus right at the bottom, it should all taste the same because it's completely dissolved in the water. It should be uniform throughout. Okay, however, if we put sand into water, we're going to see that does not dissolve. We're going to see that we can very clearly find an area in that mixture that has more sand and an area that has more water. As soon as you put sand into water, a lot of the sand is going to fall to the bottom, right? It just doesn't dissolve, and it's heavier, it's denser, so it's just going to sink. So if you look at the bottom of your sand-water mixture, you'll be able to see a lot of sand. Okay, and if you look at the top part, it's going to be mostly water. Maybe there's a grain of sand just kind of floating there or something, but by and large, you'll have different areas within that mixture. So hopefully that explains a little bit more about that. So can anybody come up with some more examples of different types of mixtures and tell me which one, if it's heterogeneous or homogeneous? Okay, I like that. Yeah, orange juice with pulp. Let me make this a little bit bigger. Absolutely. So you're going to see that slime. I like it. Okay, yeah, presumably that should be homogeneous, true. Yeah, soapy water. Well, depends. Let's talk about soap water a little bit more. Yeah. I'm going to disagree with you on soda. I like the idea, but if we think about soda, do I have a soda in here? You know what? I can go get one. This will work. Okay, kind of a soda. Okay. Look at this soda. It's not really a soda, but what do we notice about it? Wow, I've got a ton of it. Do we see areas in this soda that are different? Yeah, right? We see an area that has a lot more bubblies and an area that doesn't have as many. Right? And if we were to look at this, once it's kind of settled down, we would be able to kind of see bubbles forming on the walls right before they kind of go up to the surface. And so because, it may not be as obvious, yeah, it's going to taste the same throughout, but if you're looking at it, like one area might have more bubbles at one given time than another. So for that reason, we're going to say that soda is heterogeneous. So even those small differences, yeah, if it's not carbonated, go ahead, it's homogeneous. So flat soda would be homogeneous for sure. So, yeah, soda with bubbles, though, that's going to be heterogeneous. So let's see. Yeah, it kind of depends on the soap, and it also depends if you've got bubbles on the top. So if you do have bubbles, like if you've got soapy water that has a lot of foam on the top, that's going to be heterogeneous. However, if you've got the soap and water that's completely mixed together and there's no bubbles around, then that would be homogeneous. Okay, so sometimes it kind of just depends on how your mixture is interacting. Now I have a soda. It's not really a soda, but close enough. Alrighty, let me see if I have another example of a homogeneous mixture. I do. Well, just part of this thing. Well, you know what? Let's go ahead. Is this thing a homogeneous mixture or a heterogeneous mixture? What's it gonna be? Yeah. This. Uh-oh, Paulette is just always our contrarian, huh? Paulette, if I were to take a bite of this stapler, is it gonna taste the same if I eat this metal part versus the plastic part? I don't recommend eating staplers, by the way. Probably not a good idea. But this is definitely going to be heterogeneous because it's got multiple different things happening here. This part is more plastic. This part is more metal. This one's got kind of an even mixture of metal and plastic. This one's got more like rubbery stuff. So there's different parts of the stapler. Like we can very clearly see like this part is black, this part is silver. Like we have different areas within it. Oh, no worries. Okay, so our stapler here, if you were to just look at this metal part of the stapler, what do we think about it? It's steel. Do we think steel is going to be homogeneous or heterogeneous? Steel. Where are we going to place this? Is every bit of this steel the same if I eat the stapler up here versus down here? Is it taste the same? Again, I don't know why I'm using taste a lot for these, but yeah, steel is going to be homogeneous. Yes. So presumably if it was done properly, yeah, it's a mixture of metals for sure. So you've got iron in there, you've got some carbon in there, you've got maybe some chromium or nickel in there also. Yeah, it's definitely a mixture. We have different things going on, and they're not bonded together. So we don't have iron and carbon bonded together. They're just mixed together. And so presumably that should be homogeneous, right? Unless someone did a really crappy job of melting it and pouring it. So definitely a homogeneous mixture. Okay. Another one I'll give you is going to be air. Air is a pretty homogeneous mixture for the most part. If you were to take a look at the entire Earth, like at once, you might end up with heterogeneous air just because you'll have clouds in some parts. But if you're looking at like a room's worth of air, that's going to be homogeneous. Okay, if I take a breath from one side versus the other side, my lungs are going to be, okay, cool, we have the same amount of oxygen in, yeah, right? Yeah, totally. Or if someone, sprays perfume or something in the classroom, then it's going to be heterogeneous until it, like, completely mixes, But typically, we're going to consider air to be a homogeneous mixture. Yeah, but if you're dealing with all the ash and stuff raining in Santa Cruz and all that, yeah, that would definitely be heterogeneous. Alrighty. Any other questions about classifying matter? Alrighty. I don't see any. So let's now go ahead and classify energy. Energy is quite a bit harder because it's not something we can touch or feel. We're going to be able to see that we have kind of two kinds of energy. We're going to have what is called kinetic energy and something that is called potential energy. And yeah, plastic should be homogeneous as well. Yeah. So if you look at a plastic bag or something, yeah. So you have an interesting, it's that actually plastic is not going to be a mixture. That's actually going to be a compound. So the difference between a compound and a mixture is if you have multiple compounds or multiple elements put together that are not chemically bound together. So, for example, you can have salt is a compound, right? Water is a compound. You put two compounds together, it becomes a mixture. All right, you can have carbon and iron that are elements. You put them together, you might get a mixture. Okay, if you put hydrogen peroxide and water together, you'll get a mixture. If you put hydrogen and water together, you'll get a mixture. So anytime you're mixing two pure substances or more, you have a mixture. So it's not necessarily scale. I could have 1 drop of salt water, that's a mixture, and I could have a gallon of pure water, that's just a compound. So not really scale related, just how many different things are happening. Okay, so hopefully that makes that a little bit more clear. And so with your plastic, that's a bit more tough of an example. Something like polyethylene is technically the same compound throughout. It's just a very, very big compound. So I'm not going to ask you something like plastic because that's a bit harder to make that determination of. So let's not worry about plastic right now. Okay, so back to energy. We're going to be seeing that we can describe these as is being used, whereas potential energy could be used. So that's kind of our difference here. So kinetic energy is something that is happening right now, something in motion perhaps, or a process that is taking place. That's kinetic energy, something that's happening. Whereas potential energy is something that could happen later. Let's see if we can think of examples of each type of energy. So if we think about, let's say a car. We've got multiple sources of energy in a car. Let's think about what's happening in a car. What do we have to put into a car to make it go? A standard car, of course, not a... Well, even so, yeah. What do we put into a car? Something we worry about the price of changing makes us not happy. Yeah, gasoline. So gasoline or electricity... Well, let's just say gasoline for right now. Yeah, the oil is important too, but that's not really a fuel source necessarily. So let's not worry about oil. That's going into more like friction and physics, and I don't care about physics. So this is what is called, gasoline has what is called chemical energy. That's going to be energy in chemical bonds. And when we break those chemical bonds, we're going to be transforming that energy into kinetic energy. So what happens when we burn the gas in the car? What happens? Anybody know kind of the basic mechanics of how a car works? Yeah, exactly. So we have pistons being moved. So we're using the energy that is stored in chemical bonds to make pistons move. And the energy that the pistons are using is kinetic energy. So we have released the energy from its potential state and transformed it into kinetic energy. So we took potential energy, we could have used it. Gasoline, if it's just sitting there, it's sitting there, it's not doing anything. But if we kind of get the process going, we start igniting it, we transform that energy to make pistons move. And the motion of those pistons moving, going up and down, is going to be kinetic energy. And that kinetic energy is used to turn the motor, which turns the wheels, and off you go, driving to Las Vegas to go gamble away your life savings. So that's how kind of the difference here. So kinetic energy is going to be stuff that's happening right now, but potential energy is something that is could be used for the future. Another example is, let's say you're a supervillain. All right. Okay, and you have some helpless victim down here, and you're on top of the mountain here, and you have a rock with you. That rock has, in this case, what is called gravitational potential energy. So we could use the energy in this rock to do something. And being the supervillain that you are, just merciless and cruel and just evil, you could use that gravitational potential energy to transform it into kinetic energy, right? If you push this boulder a little bit, you could use that energy to make the boulder move, right? If you just give it a nudge, the gravitational energy within that boulder will force it to move, right? If you push it, it's going to roll down the hill. And because you're evil and mean, you're going to try and squish the person down there. And so, by releasing the energy, the boulder rolls. Oops. And you could use that kinetic energy of the boulder rolling to do something. So we use the chemical energy in gasoline to make our pistons move. This case, with gravitational energy, we're using it to squish someone. Okay, by giving that or allowing the boulder to release the energy as kinetic energy. Okay, so these are just a couple of examples, but we see that kinetic energy is something that's being used. It's happening. Something is moving, essentially. Potential energy is just going to be sitting there until we release it. Okay. So does that kind of illustrate the difference between potential energy versus kinetic energy? So potential energy, nothing's happening, but stuff could happen. Kinetic energy, stuff is happening, energy is being released, something is moving, things are happening. All right. So it looks like we're kind of out of time for today. So tomorrow we're going to be talking about more stuff about matter. We're going to talk about, solids, liquids, gases, and we'll talk about how we can separate things, different types of matter and that. So any final questions before we end for the day? Of course, if you are watching this later, you're totally welcome to post questions in Discord. Be like, hey, can you explain this thing again? Or, I thought about ramen as a mixture. Can you help me if it's heterogeneous, homogeneous, whatever? Definitely help each other out. And I will, of course, be there to, provide guidance as well. Okie doke. Looks like we don't have any, so I will post these as well. So I'm gonna go ahead and in Discord, let me see here. I'm gonna go ahead and let's see. We are in. Let me load this up. Okay, we are in 101, right? So I'm gonna go ahead and upload this file of my beautiful drawings and lovely stuff to our Discord. So it is going to be here. Let's see. I'll upload it. So you'll be able to see the lecture notes in this channel here once I've loaded them. Okay? Just one thing, I'm going to make it so you guys can't post stuff on this. You guys can read messages, but you cannot send them. Okay, blah, blah, blah. Nope, no assignments yet. So you'll be okay for now. Alrighty. So I'll see you guys all tomorrow. Enjoy the rest of your day. Have fun.